Okay, so for the next talk, we have Noah Zilberman, who's going to tell us about semi-classical backreaction of the Cauchy horizon, the non-evaporating case.
Thank you very much. And thank you so much to the organizers for inviting me. It's actually non-trivial that I'm here because our car totally broke down on the way. And we had to be towed, and my son was very excited about it. And then we were stuck in Ithaca for a few days, and the Hebrew word for being stuck is lahitaka. So that was quite fitting. And if that's not enough, we also forgot our passports at home. So I would like to thank Maxime and Weihao especially for helping out. So it's great being here today. Two more comments before I begin. This is a physics talk. So I won't pretend to be a mathematician. I'm a physicist, a postdoc at the Princeton Gravity Initiative. So apologies in advance for the lack of rigor, although the math I'm going to use is kind of kindergarten level for you. And second thing, so I think some of the people here heard me in the Simon Center a year ago. So this is the same topic, but a different talk. This one is more detailed. Okay, so without further ado, I will begin. I just want to mention this is based on a work with Amos Ori, who was also my PhD advisor. And we're working on a paper, on that topic. So I will start with a short story with an open end. The analytically extended Riser-Nordstrom and Kerr spacetimes, which correspond to a spherical charged or spinning black hole, have an inner horizon from which you can maybe even get to another universe. And this remains the case in the more physically realistic scenario of gravitational collapse, in which the ingoing section of the inner horizon maintains the role of a Cauchy horizon, being the boundary of the domain of predictability for initial value problems formulated outside the black hole. So imagine there's a traveler that wants to explore these regions of space-time. In order to do so, she must pass through the black hole interior, and in particular through the Cauchy horizon. And the question is, what will she encounter along her way? And does this other external universe even exist? So in order to understand these questions, one would need to understand the manner in which quantum effects modify black hole interiors. But it is already known classically. Today we were actually talking a lot about that, and I want to thank the other speakers today. So today we were talking about the Cauchy horizon. So it was already known classically, as you heard, that the Cauchy horizon under classical perturbation is not regular, and it is actually a weak null singularity. It is weak in the sense that the metric is continuous, C0, but not differentiable, not C1. Or in physical terms, it is not tidally destructive. And I put a bunch of references from the physics literature and from the math literature, many people who are here today. So both in the spherical charge and in the spinning case. And this is reflected in TVV. So V here is a Kruskal coordinate. It's a coordinate regular at the Cauchy horizon that vanishes there. So this irregularity is reflected in TVV by this, maybe I can, do you see? Okay, nice. So by this V to the -2 divergence, but with a logarithmic softening. So this logarithmic softening makes this singularity a weak one. And it is related to how perturbations decay outside the black hole, or in other words, the Price law that you know about, and how they evolve inside. By the way, the Price law does not exist for quantum fields. So this is not anticipated to carry to the quantum case. Okay, so this raises the question, do quantum perturbations induce a stronger singularity at the Cauchy horizon? So because I am asking questions about quantum matter fields propagating on a classical curved spacetime, a suitable framework is the semiclassical framework of GR. So you all know the Einstein equation. In semiclassical GR, we add another source. So that is the renormalized stress energy tensor. This is the semiclassical Einstein equation. So we have the usual classical source. It can be 0 if it's vacuum, like Kerr. But we also have a renormalized stress energy tensor that is an expectation value in some quantum state. So the idea is that space-time curvature induces a non-trivial stress tensor in the quantum fields, even in vacuum states. And these, in turn, deform the metric. So you can think of it as two directions. The metric induces some non-trivial stress energy in quantum states, and these deform the metric by taking this route of backreaction. And this effect, this quantum effect, is very tiny when you consider it locally. So we have this H bar here, H bar because it's a quantum effect. I don't know how many of you, I don't know some physics maybe. Or like quantum physics, okay, that's a different kind. But anyway, H bar is the scale of quantum effects, and 1 over m squared is the scale of curvature of the geometry. And it is, I call it epsilon. This is the small parameter that I will use throughout. And for astrophysical black holes, for black holes that are more massive than say 3 solar massives, this is extremely small. This is 10 to the minus 77. So this number is very, very small. So when you include these quantum effects and look what they do locally, then it is an extremely small and negligible effect, but these effects can accumulate over extended timescales. And then they can lead to significant global effects. And a famous example is Hawking radiation. So in the Hawking effect, backreaction effects accumulate along the event horizon and lead to a drastic reduction in the horizon's area as the black hole evaporates, and contradicting classical expectations. So this is just one example in which quantum effects can dramatically change the classical space-time picture, especially when considering black holes. So this motivates us to look at what do these quantum corrections do at the Cauchy horizon. Now, the way we are going to treat this semi-classical Einstein equation is iteratively. So each iteration has 2 steps. The nth iteration, so this is a notation of using the metric that arises from the previous iteration. So evaluating the Einstein tensor and the classical stress energy tensor in the previous iteration, and then solving for the nth order semi-classical tensor or renormalized stress energy tensor. And then in the next iteration, in the next step of this iteration, you solve for the metric. Okay, so first you solve for the renormalized stress energy tensor on the metric of the previous iteration, and then you solve for the metric by feeding it into as a source in the Einstein equation. Okay, and this talk is about the first iteration, the n equals 1 iteration. Okay, so the talk plan. The first half of the talk is going to be about the first step of the first iteration, in which I will tell you some results about the first order stress energy tensor computed on some fixed classical 0th order black hole spacetime in 3+1. And the second half of the talk would be to feed this as an input to the second step of the first iteration and to compute the geometry, how the geometry reacts to this new source. Okay, so the first part. So now let's talk about the first order stress energy tensor at the inner horizon. So there has been a bunch of analytical hints that accumulated throughout the years that the semi-classical stress energy fluxes are likely to diverge at the Cauchy horizon, but it has not been shown conclusively. So our goal has been to address this issue through concrete computations, and we did it both in the spherical charged and then in the spinning case. So first, well, the background metric we are eventually would like to study Kerr. So, but as you know, it is a toy model to start with Rising-Nordstrom. So charge is a poor man's angular momentum, a quote by John Wheeler. So we start with Rising-Nordstrom, which you all know, and then we also do Kerr. Okay, I'm going to go a bit quickly and get to the results. So these are my 0th order metrics, either Rising-Nordstrom or Kerr. And on these geometries, I introduce a field. So I take a minimally coupled massless scalar field, which obeys the Klein-Gordon equation, and then we treat it as a quantum field, which means we upgrade it to be an operator. And it obeys the same equation. The modes obey the same things that you know classically. And the thing about quantum fields is that you need to assign a state to the field. So there are some quantum states that you can take on a fixed static eternal black hole background. There's the Hartle-Hawking state, which corresponds to a black hole coupled to a thermal bath. This is a static state. It is time reversal symmetric and time translation symmetric. And then there's the Unruh state, which mimics the formation of a black hole in gravitational collapse. And as a result, it gives rise to Hawking radiation and to black hole evaporation. Okay, now the flux components that are related to this scalar field, TUU and TVV. So just to introduce some coordinates. So the V coordinates, the Eddington coordinates are just the usual null coordinates. And then we have the Kruskal coordinates, which regularize the event horizon. So TUU and TVV, you can think of them as TVV as an influx or ingoing flux, and TUU as an outflux, like the arrows here indicate. And then let's focus on the black hole interior. So first, from regularity, TUU at the event horizon has to be 0, because otherwise, if you go to the Kruskal U coordinate, which vanishes at the event horizon, you get that it diverges like q to the -2. So from regularity of these states at the event horizon, you get that TUU in Eddington coordinates has to vanish there. Okay, what about TVV? Now, energy momentum conservation yields a conserved quantity, an R-independent quantity, TUU minus TVV times an area component. And this coincides with Hawking radiation per unit solid angle, where you take it to infinity. So in the Unruh state, which corresponds to an evaporating black hole, this is positive. So at the event horizon, you have a negative TVV. Oops. At the event horizon, you have a negative TVV in the Unruh state. So that's why I only drew, I can maybe use my hand. I only drew some influx coming through the event horizon, no outflux. But this can develop because of the curvature of spacetime to the Cauchy horizon to have both TUU and TVV at the Cauchy horizon. Similarly, in the Hartle-Hawking state, in which the black hole does not evaporate, this state is static, then TUU equals TVV everywhere, which means that at the event horizon, you also have TVV vanishing in the Hartle-Hawking state, in this homogeneous state. And then despite having no influx and no outflux at the event horizon, again, because of the curvature of spacetime, the field evolves, and you do have a TUU and a TVV at the Cauchy horizon in that state as well. Why are we interested in these flux components? So TVV is especially important at the Cauchy horizon, because just like having a non-zero TUU at the event horizon gave rise to a singularity there, having a non-zero TVV in Eddington coordinates at the Cauchy horizon would give rise to a singularity there when viewing it in terms of regular Kruskal coordinates. But it's important for me to say that this divergence that I show here by itself is only taken on a fixed background, on a fixed Rising-Nordstrom or Kerr background, and it does not imply that the Cauchy horizon is replaced by a strong singularity. In the back-reacted geometry, this is not the whole story. You need to actually perform the consistent back-reaction analysis. But this is just what was driving people. Okay, so now what is the stress energy tensor? You all know the classical starting point for a scalar field. The trace reversed is just simpler because it has just this product. It doesn't have this extra term. And now the quantum version, one would think, okay, let's just put expectation value. It turns out that this diverges. but it includes all the information we need. So I call it bare. Bare means it's prior to renormalization. So it's a formal expression. So this T muni bare is just this expectation value, and the flux components equal to the trace reversed flux components equal to this product of field derivatives. Okay, but yes. So the expectation value of phi itself is 0. Yes, it's only when you combine quadratically you get non-zero things. Yeah. Okay. So it turns out that this thing looks nice. You're used to working with it classically, but in the quantum context, this formally diverges and requires renormalization. And this happens already in flat spacetime. It doesn't have to do with the curvature. But in curved spacetime, it's much harder. So I will not say anything more about renormalization. I will just say it's very hard. It's very subtle, both analytically and numerically. And it was a main challenge in the field for decades to perform these computations in 3+1 black hole backgrounds, especially to formulate a renormalization scheme in 3+1 in a curved spacetime. That's very hard. Okay, but it's possible. So here are some results. Okay, so I'm jumping straight to the results for the semi-classical fluxes at the inner horizon. We'll start with the charge spherical case. So first we computed TUU and TVV in the Unruh state, as well as in the Hartle-Hawking state. Recall in the Hartle-Hawking state, TUU equals TVV. That's why I only have one quantity here. And this is in logarithmic scale. So you see that and this is as a function of the charge of the black hole. So you see that as the black hole approaches closer to the Schwarzschild domain, the fluxes are very large near the Cauchy horizon, which kind of makes sense. And then there's a sign change here, and they change sign. So let's look at this sign change domain. So all of these three quantities, they are positive below some critical Q over M value, and they are negative afterwards. And this is very important. Okay. The sign is going to be very important, you will see. And also they all approach 0 as extremalities approached. And it turns out that we can treat analytically this near extremal limit and actually find exactly how these different quantities behave on approaching extremality, but I will not go into it. And now let's go to the spinning case. Okay. So similarly, so in the spherical charged case, we only had one parameter to worry about, which was the charge, or Q over M. In the spinning case, you have two parameters. You have the angle, the theta angle, and you have the spin of the black hole. So first we fix theta equals 0. So we are looking at the axis of rotation. And again, here we see the fluxes as a function of the spin of the black hole. A is the spin parameter of the black hole. And we see that there's a sign change at some critical value. So that's interesting. This looks a bit like the Reiser-Nordstrom case. Again, we have the approach to 0 with extremality, which can be studied analytically. Okay, now let's go off the pole. So not look only at the axis of rotation, but also look as a function of theta. So here we fixed a certain spin value, 0.8, and we present the fluxes as a function of theta. So it starts with some positive value on the axis of symmetry, and then it changes sign twice. So that's also kind of interesting, and we had no expectation for this behavior. Okay, and you can also compute the fluxes away from the inner horizon and see how the asymptotic values at the inner horizon are approached. And we did it also in another paper. Okay, and you can also compute in between the horizons. So here you see the fluxes between the horizons, how they change sign also from the inner horizon to the outer horizon. They have a negative domain and positive domain. And all this is very interesting, especially the sign, because there was no analytical expectation for what the sign of these fluxes would be. And the sign is very important for backreaction. So it required numerical computation. So the summary of the first half of the talk, both fluxes, TVV and TUU, at the inner horizon attain well-defined generically non-vanishing values. Both of them vanish at different rates, which can be studied analytically as extremality is approached. And in particular, on a fixed Kerr or Reisen-Nordström background, so not taking backreaction into account yet, you get this v to the -2 divergence in Kruskal coordinates at the Cauchy horizon with generically non-vanishing coefficient. And this coefficient can have either sign, positive or negative, based on the black hole parameters, the charge, the spin, and the angle in the spinning case. And this sign is going to be crucial for backreaction. Okay, so that was the first half of the talk. If you have any questions so far, I'm happy to answer. Okay. Yeah. You will see. Or spoiler, both are bad, but different kinds of bad, I guess. Yeah. Okay. So the second part is backreaction. I guess that's the main part of the talk, or the more important part of the talk. Everything I showed you so far is just as an input to this backreaction analysis. So the question we ask now is, what replaces the classical Cauchy horizon once the first order stress energy tensor is allowed to backreact? Okay. So we did the first half, the first step of the first iteration, and now we're going to feed what we found here into the as a source of the semiclassical equation to find the geometry that arises in the second step of the first iteration. Okay, so the setup in which we are working is first spherical symmetry. We focus on the spherical charged case. I showed you previously results both for the spinning case. That is irrelevant for that part of the talk. So we take Reisen-Nordström as the 0th order metric here. And the quantum state that we consider is the Hartle-Hawking state that I mentioned before. Importantly, you don't need to know the specifics, but you need to know that it is a homogeneous state. So that means that it is static, it is time reversal invariant. The black hole does not evaporate in that state, right? Evaporation would violate the staticity of the state. So it has a fixed m mass and a fixed charge for the black hole, and TUU equals TVV everywhere. So the influx equals the outflux at every point of spacetime. Okay, so this is the state we are going to work with for simplicity. As a first stage, yeah, okay. Now the backreacted metric is what we want to solve for. So first we take a general spherically symmetric metric in double null coordinates. I write it in this way. U and V are the coordinates that are induced by the usual Eddington coordinates at the event horizon, where we do have a Reisen-Nordström metric. So this is the radial subspace, this is the angular subspace, and at 0th order, the Reisen-Nordström interior, you can think of e to the sigma as minus f, and at the inner horizon vicinity, sigma comma u of v is minus kappa minus, which means that e to the sigma decays exponentially. So GUV decays exponentially with R star. And R comma U of V is of course 0 when R is close to R minus. Because R is just constant there. And if I were not to write here 0, I would write something exponentially vanishing. Okay. So our goal is to solve for the metric functions sigma and R of the backreacted metric. So we want to solve this equation, the semiclassical equation sourced by the first order stress energy tensor. And we want to solve for the first order geometry. Okay, so first I need to tell you what is this guy? This is the electromagnetic stress energy tensor. Just in the classical background, you have this electromagnetic stress energy tensor. It has the following form. So the minus sign here, so it goes like the metric, but with a minus sign when mu and ni are u of v, and with a plus sign when mu and ni are theta of phi. In other words, it is traceless, and this is what it looks like for this metric. And I want you to notice that the stress energy tensor has an electromagnetic contribution and a quantum contribution. So you can say, okay, the quantum contribution is tiny, so how can it do anything? But note that the TUU and TVV components of the classical stress tensor are zero. So the quantum contributions to these terms are dominant. So they're not, they are tiny, but they drive the dominant behavior. Okay, so now I'm going to introduce alternative metric functions. I will call it capital R and capital S. They are related to the R squared and sigma in the following way. It turns out that it's nicer to work in these coordinates, and these are the Einstein equations that we get in these coordinates, R and S. So we have two evolution equations, and we have null constraints. In the evolution equations, this FR and FS just come from they encode the electromagnetic classical stress tensor. And then on the right-hand side, I put all the quantum stuff. So all the quantum sources are on the right-hand side. This ZR is the source for the R equation. ZS is the source for the S equation. And you can also see that the sources for the evolution equations are just T theta theta and TUV. And the fluxes only enter the constraints. The fluxes TUU and TVV. Okay, so now we are going to analyze R and S. So first, from homogeneity, again, TUU equals TVV, and V derivatives are Y derivatives. And so all these equations can be reduced from PDEs to ODEs in the homogeneous case. Okay, so instead of, I had UV before over here and over here. Instead, I just have YY here. Y is either U or V. Okay, so I just have ODEs at this point. This is a major simplification that happens in the homogeneous case. Now, I want to tell you some stuff about these sources. What is the effect of the semiclassical sources at the inner horizon vicinity? So in order to understand that, let's first ignore them. So let's first do Reise-Nordström. Reise-Nordström is exactly the same system of equations, but with no quantum sources. So in the Reise-Nordström case, I just deleted the quantum sources on the right-hand side. So at the inner horizon vicinity in Reise-Nordström, we know exactly how S behaves. S comma R star is -2 kappa minus. So at the inner horizon vicinity, e to the S decays exponentially, and you can get rid of these two terms. Okay, so this is very, very, very easy. That's why I said kindergarten level math. The solution is just a linear solution. R star here is U plus V over 2. That's how it is defined. Okay, so we get a linearly drifting behavior for both R and S with R star. And in Reise-Nordström, we know exactly what these coefficients are. So we have 4 coefficients. For R, which is R squared, small r squared, the coefficients are just, you have just R minus squared because you're at the inner horizon. And importantly, the linear drift coefficient vanishes. For S, the linear drift coefficient does not vanish. It is -2 kappa minus. Okay, so this is the behavior in Reise-Nordström. Okay, and then of course in Reise-Nordström, the constraint is trivially satisfied. So this is Reise-Nordström. I showed it just to contrast with what we're going to find in the back-reacted case. Okay. So I do want you to notice, I don't know if you see it very well, I'm highlighting the fact that this is 0. So the linear slope is 0 in Reise-Nordström for R. For S, it is non-zero. It is some finite order 1 value. Okay, so the linear coefficient of R near the inner horizon Reise-Nordström vanishes. And now let's go back to the back-reacted geometry. Let's see what happens there. So in the back-reacted geometry, we're going to do an ansatz now. So based on the Rising-Nordstrom behavior we just saw, and the fact that the semi-classical sources are very tiny, they're of order epsilon, we expect that in the backreacted geometry, the function S still diverges to minus infinity on approaching, or when R star is very large, or when U and V are very large, linearly with R star. Okay, so this is the ansatz. That S, just like in Rising-Nordstrom, it still diverges linearly to minus infinity with some coefficient. And later, a matching argument that I will not show because it's kind of almost trivial and technical will show that this coefficient is just kappa minus plus some epsilon correction. Okay, so we will use the following thing as the ansatz, that S comma R star, the derivative in the R star direction, is minus kappa minus, just like in Rising-Nordstrom, plus some epsilon correction. And importantly, okay, so we're just going to add an epsilon correction to the Rising-Nordstrom behavior. And importantly, e to the S is still going to vanish exponentially. So now, what can I tell you about these semi-classical sources? The fluxes that appear in the constraint equations are just constant at the inner horizon. The trace reversed angular component T theta theta is also just constant. I didn't tell it before, but I can tell you now that semi-classical analysis shows that it's also constant at the inner horizon. But notice that it is multiplied by e to the S everywhere. So this is the source of the R equation. This is the source of the S evolution equation. And T theta theta is multiplied by e to the S. So it is going to drop out asymptotically. And what about TUV trace reversed? Well, again, an analysis shows that TUV behaves like R star to the minus 4. So it also drops out asymptotically when R star is very, very large. So we see that semi-classical analysis yields that both these sources are negligible. Okay, so this is one step. The next step is what happens to these two. Well, now let's go back to the ansatz. And again, according to the ansatz, S still goes to minus infinity linearly with R star. So e to the S vanishes asymptotically. And we also can get rid of these terms. Later, I will show that the ansatz remains consistent. Okay, so we are back to the same equations almost. So in Rising-Nordstrom, we also had these two evolution equations, but in Rising-Nordstrom, the null constraints didn't have a right-hand side. Okay, so this is exactly like Rising-Nordstrom in the vicinity of the inner horizon. So we get the same linear behavior with some general coefficients, C0R, C1R, C0S, and C1S. So first, for S, you see that we got that the ansatz is consistent, right? So we got a linear behavior of S, and the C1S is just determined by the ansatz. Okay. Now, what about the R? Again, R is the area of two spheres. What about this function? We see that it has this potential linear drift. So the evolution equations, so far I only worked with the evolution equations, they gave rise to the linear behavior. And next, we are going to use the constraint equation to fix the slope of this behavior. So just put both of them on the screen. The evolution equation gave us this, and the constraint is the following. So first, because R is linear in R star, this thing vanishes. Okay. Second, from the ansatz, this minus S comma Y is just minus kappa minus, so we can replace it. And finally, I'm going to replace this by its near inner horizon value. Okay, and I got that C1, so this coefficient C1R before the R star, it's R comma R star, which means it's twice R comma Y, which I can read up from there. So I got C1. And I want you to notice again that in the Rising-Nordstrom solution, which I put here on the left-hand side, then we have the following. We have that R comma Y is 0. It's not this finite value. It's some 0 value. And this, and in particular, the linear coefficient of R near the inner horizon in Rising-Nordstrom vanished. So just compare these two. This is non-zero, and this is 0. And this gives rise to the following behavior. So the coefficients C0R and C1R are determined up to higher order epsilon corrections, and you get the following behavior. So R, the area of two spheres in the regime of large R star is the following. This is the order epsilon small thing, okay, that we computed. So what do we get here? Okay, and I want you to also notice the following fact, that this is very, very different from the Reisen-Nordström behavior, although the behavior for S is very similar. So just notice the following fact, that in the Reisen-Nordström solution, which I wrote here, R, Y is 0 and S, Y is some finite thing. So it makes sense that if you add epsilon correction to the S, Y, you're not going to get much change. But if you add a small correction to something that is 0, you are going to drive a very dramatic change in the geometry. So this is what happens. So this is a strong singularity. So that means that in the back-reacted geometry, the Cauchy horizon area, or the area of two spheres on approaching the Cauchy horizon, drifts like R star. And in particular, this is where you see that the sign is very important to your question, Jakob. And it's kind of a choose your own terrible adventure. So if the fluxes are negative, then you see that the Cauchy horizon area diverges to infinity in the large R star regime. And if the fluxes are positive at the inner horizon, then the area shrinks to 0. So that is a strong singularity. I will explain this minus afterwards, which means that the metric is not even continuous. It's not even C0, unlike the classical case. So this is stronger than the classical singularity. It is tidal destructive, unlike the classical singularity. For example, if you consider two radial geodesics separated by some azimuthal distance, you get that the distance between these geodesics will either go to 0 or to infinity at finite proper time. And I will explain this finite proper time soon. Okay, now before I go on and talk more about these two different scenarios, a quick note on the event horizon. So our analysis at the inner horizon yielded the following. You may ask, what will a similar analysis yield at the event horizon? It's supposed to be very similar, and indeed it is very similar. So a parallel analysis at the regular event horizon yields the following. Okay, this looks alarming. We know that the event horizon is regular. So what happens? I want to remind you. Okay, so we have that an accumulating effect can in principle appear at the event horizon of the back-reacted geometry, but recall that from regularity of the event horizon, this is 0. Remember, I showed you before, I showed you this picture and I said that there's nothing coming from here. So actually, in principle, you could have a slope, but it is 0. So in the event horizon, you just get the result you expect, and in the inner horizon, you get the full drifting behavior. Okay, another visualization of the result. So we have a slope, which is very tiny. So what is the behavior of R, which is again defined as R square, or the area of two spheres near the inner horizon, or at large U and V Eddington? So in Reisen-Nordström, it's just a constant. In the case of negative fluxes, it's a positive slope. It's a very tiny slope, but it accumulates. And likewise, in the case of positive fluxes, it's a negative slope. So you see that a very tiny slope can accumulate over as much as we want, right? Because R star go all the way to infinity. And then an accumulation can turn order epsilon sources into order 1 geometry change. This is also what happens in Hawking effect, for example. So if you go to R star of the order of M over epsilon, where epsilon is the small parameter governing the slope, you're going to get an order 1 geometry change. Okay, so I hope I showed you that the sign is crucial. Yeah, so for example, here, this is a plot I showed you before, again, of the fluxes at the inner horizon. Focus on the green one, on the green line. The green line shows the Hartle-Hawking flux at the inner horizon as a function of the charge of the black hole. And you see that depending on which black hole you jump into, you can either have positive fluxes and shrinking spheres or negative fluxes and expanding spheres. So it really, your fate depends on the parameters of the black hole. And there is some critical value, which above it and below it, you get the expansion versus the contraction. Okay, so now I will talk a bit about the two singular outcomes, which are determined by the sign of the fluxes. Okay, so case one, if Q over M is larger than the critical Q over M value, then the fluxes are negative and you get an expansion. So this is a reminder here at the bottom of the behavior. So where is the singularity located? Okay, you have R goes to infinity. You may ask, do I reach it in finite or infinite proper time? And is it null, space-like, time-like? Okay, so it turns out that despite this R goes to infinity divergence, the singularity actually occurs at a finite location in the space-time manifold, or in other words, how do we quantify this? It is reached by infalling observers within finite proper time. So to substantiate this claim, let's look at geodesics in the backreacted metric on approaching this singularity. So this is the metric. This is the geodesic equation. And for simplicity, we focus on radial geodesics in the equatorial plane. And the only Christoffel symbol that enters is this one. Again, y is either u or v Eddington. So we see that we have two terms. So I'm going to compare this Christoffel symbol in the 0th order metric and in the backreacted metric at large R star. So first we saw that at large R star, meaning near the inner horizon in Reiser-Nordstrom, S comma u of v Eddington is minus kappa minus. And from our ansatz, this is also the same for the backreacted metric, ansatz plus matching argument. What about this term? We know that in the backreacted metric, R comma y is non-zero. In the Reiser-Nordstrom metric, it is 0. Okay, but in the backreacted metric, R goes to infinity. So you can have a vanishing of this term either via the, what's it called, numerator or denominator? Thank you, this one on top vanishes in Reiser-Nordstrom, and this one going to infinity, both of them yield the same value. So that means, that's very interesting, that we found that the Christoffel symbols are actually the same for Reiser-Nordstrom on approaching the Cauchy horizon and for the backreacted metric on approaching the singularity. The same Christoffel symbols means same behavior for geodesics in that asymptotic domain. And the semiclassical fluxes don't enter at all. Okay, so that means, so this is Reiser-Nordstrom. So Reiser-Nordstrom, you can imagine geodesics approaching this inner horizon. So just like for geodesics that approach the inner horizon in Reiser-Nordstrom, then radial geodesics in the backreacted metric also reach the R goes to infinity singularity within finite proper time. They have the exact same properties, and it is null for a similar argument. And you can show it in more details, but you just get the key thing is that geodesics behave exactly the same as in Reiser-Nordstrom, and you get that the backreacted metric has a null strong singularity in that case, which is reached within finite proper time. So it is located at V Kruskal equals 0. It's a finite location in the manifold. Okay. Now the other case in which Q over M is smaller than the critical value, then the fluxes encountered at the inner horizons are positive. And in that case, we have the shrinking, again, because of this minus before the slope. So this is clearly a space-like singularity at R equals 0. But if you were paying attention, we were neglecting some terms along the way that went like 1 over R, or in other, or more specifically, like e to the s over powers of R. So how close can we get to R equals 0 before our assumptions break? It's clear we cannot go all the way to R equals 0. And it turns out that our approximations hold as long as R, so the area of two spheres, is still larger than e to the minus 1 over epsilon, reminding you that epsilon is like 10 to the minus, sorry, e to the minus 10 to the 77. So this is an extremely, extremely, extremely small number, probably the smallest number I've ever written. So this means that our approximations hold until we are extremely close to r equals 0. And actually, the semi-classical approximation fails way before that. So I'm not claiming to go all the way to the r equals 0 singularity, unlike the things that we heard yesterday on the BKL, Kastner, and so on. I'm not in that regime at all. And that's why I put a plus over there. So the semi-classical solution does not literally reach the r equals 0 singularity, but it does reach an effectively singular region. So I call it an effective singularity. And that's the validity that's the domain of validity of this analysis. So this is the space-time picture that we have in that case. So these are the two different scenarios that we get depending on the signs of the fluxes at the inner horizon. Either a strong space-like singularity in the case of positive fluxes, or a strong null singularity in the case of negative fluxes. Okay. And maybe to people who are used to the classical world, this looks strange, but this might also look strange to you, the fact that fluxes can be negative, right? So yeah, quantum is different than classical. Okay, now a bonus topic is a few words on backreaction in the evaporating case. Yes. Yes, please. Very good. That's exactly the next thing I wanted to say. Yes. Okay. In a homogeneous case, no. In a homogeneous case, these are the only two different cases that you can have, because Q over M is fixed and this number is fixed. So it's either negative or positive. And I'm happy nobody asks me about what happens when it's strictly 0. But if you want, you can ask me later. Okay, so a bonus topic is what happens in the non-homogeneous case. So far, we only talked about a homogeneous, the homogeneous scenario in which the black hole cannot evaporate, TUU equals TVV, the influx and the outflux cancel each other perfectly in every location. That was, of course, not very realistic, but it was one step towards a better understanding. So a few words about what happens in the non-homogeneous case in which the black hole does evaporate. So I'm going to go back to the story I started with our traveler and what happens to her. So, so she reaches the Cauchy horizon, and then I asked, what is her fate? Is her mission doomed to fail? And it seems from what I showed you so far that yes, she's doomed, because she encounters a strong singularity. But in the non-homogeneous case, the Unruh state that I mentioned before, there is evaporation in the background. And this needs to be taken into account when considering, when evolving the Einstein equations from the event horizon to the Cauchy horizon. In the homogeneous case, the event horizon was strictly Weissenotstrom. In the evaporating case, the event horizon has drifting M and Q parameters based on the evaporation. So it's much, much harder. And these two steps are causally related. So an illustration in the Weissenotstrom case, we can talk about the soft stage of backreaction in which there is evaporation in the bulk. So this is a very slow drift in the black hole parameters along the event horizon. So M and V are now functions of, I'm sorry, M and Q are now functions of V along the event horizon. So this is straightforward to analyze on its own. But then there's the hard stage, which is the sharp distortion that we saw due to tidal effects near the Cauchy horizon. And these two are causally related. So imagine our traveler jumping into a black hole with some Q over M value. And as she approaches the Cauchy horizon, she is exposed to drifting Weissenotstrom geometries. So to drifting M and Q values. So that also means that she is exposed to different flux values, because as you remember, the flux dependent on the black hole parameters. So the black hole parameters drift and the fluxes drift as well. They're not fixed anymore. And when she approaches the Cauchy horizon, she is already exposed causally to a very different black hole from the one that she jumped in. So that is a stark difference from the homogeneous case. Yes.
When you say drifting, it's just like drifting to zero?
No. Okay, so it really depends on the evaporation that you take into account. Yeah. For example, in the Reisen-Nordström case, if you only evaporate non-charged particles, then your black hole is not going to disappear. It's going to drift to extremality. So it really depends on what matter fields you take into account. So anyway, thank you for asking this question, because this shows us that what happens at the Cauchy horizon really depends on what happens along the event horizon, or in other words, what is the evaporation model we take into account. Yeah, so there's a causal effect between the soft and the hard stages. They both contribute to the same order in the perturbation theory. So we need to take both into account. Just to give you a taste, just like I wrote before, the constraint equations that gave me the slope in the homogeneous case. In the non-homogeneous case, I can also write down these equations. Now I have an equation for U, which is along the Cauchy horizon, and an equation for V, which is along an outgoing geodesic approaching the Cauchy horizon. And it seems like it's going to be very similar to what I showed you in the homogeneous case. But in the homogeneous case, the right-hand side was fixed because the black hole parameters were fixed. So everything here was fixed. But now it's not fixed anymore. So the right-hand side now is a function of the point you are at, what local geometry you are exposed to. This changes the kappa minus, the r minus, and of course, the flux computed on that geometry. So things are going to be very different. Okay, so again, I show this plot, this time focus on the red and the blue plots. So you see that TUU in the non-homogeneous case and TVV, they also change sign, and the sign again is very important, but they change sign at different points. So for example, here you have both TUU and TVV positive, here both of them are negative, and here one is positive, the other is negative. And then to your question, Hamed, we have some in the non-evaporating, in the evaporating case, the non-homogeneous case, we have some function Q over M as a function of V. So as I approach the Cauchy horizon, I'm going to make some journey along this axis. And then sometimes I'm exposed to negative fluxes, sometimes I'm exposed to positive, sometimes one is positive, one is negative as I approach the Cauchy horizon. And this can give rise to the scenario you were asking about. So this can give rise to a singularity that starts space-like and then becomes null. So imagine I start here, I jump into such a black hole, and then it evaporates to extremality, and then I'm suddenly here. Suddenly I'm exposed to negative fluxes, which expand me and take me from the space-like to the null. Yeah. I think so, yes. Like if you start here and drift over there. But this is all I'm saying now is very preliminary. This needs to be studied. Yes. Okay. But I do want to say that a preliminary analysis, so as I answered to Yaakov, the analysis here really depends on what evaporation model you take into account. And you can consider different models. And in some model that I considered, in which the black hole evaporates to extremality, so the Q remains fixed and the mass goes down to Q. So in that case, I found a weak singularity, not a strong one. So the non-homogeneous case is very different from the homogeneous case. And it is more realistic, so it is very interesting to see what kind of singularity we are going to find there. Okay, summary. So we studied semiclassical backreaction at the Cauchy horizon of a charged spherically symmetric black hole at first iterative order. Everything I said was just to first iterative order. I didn't tell you anything about what happens at the next iteration and whether these iterations even converge. One would need to study that question. So this was only for a first iterative order. Yeah, so in the homogeneous non-evaporating case, The semi-classical Einstein equations admit a very simple analytical solution. You saw we had just this linear drift of the two-sphere area. And we only needed the evolution equations to give this linear form. And then we needed the constraint equation to fix the slope. The classical Cauchy horizon does not survive as a regular null surface. And it is instead replaced by a tidal destructive strong curvature singularity, which is not even C0. And depending on the sign of the fluxes, or equivalently on the charge to mass ratio, the singularity is either null with an expanding two-sphere area, or space-like with a collapsing two-sphere area. And in both cases, the singularity is reached within finite proper time. So that is a dramatic consequence for our traveler. And I hope I convinced you that the sign is very important and that the sign is non-trivial and you cannot just guess it. I mean, you can guess if you want, but in order to actually know the sign, you have to perform a very delicate numerical computation and regularization. So that was the first half of the talk. And then the non-homogeneous or evaporating case is more subtle and more interesting, and it is a work in progress. Future directions, okay, to abandon spherical symmetry, to consider spinning, to abandon homogeneity, to consider the non-homogeneous case in which we don't have ODEs but PDEs, and we don't have fixed black hole parameters, but the black hole parameters are functions of V along the event horizon, and the black hole does evaporate, and TVV does not equal TUU. So there are many, many complications in that case, but we already have some preliminary result in that case. Okay. Also, it would be nice to mathematically explore this system, and Maxime and I started talking about these things. Okay, that's all. Thank you very much.